Hello, welcome to the session on design of machine elements. In this session, we will see the simple stresses acting on machine element. We have the simple stresses. One, it is a tensile stress. Then we have the compressive stress and it is the shear stress. So stress, it is the resistance offered by a body to the external force to the unit area. So let us see the tensile stress first. So here we have a rectangular bar and that is acted upon by an external force that is tensile in nature, and the force is represented as capital P. So the area which is resisting the force is this rectangular face, or it is same as this rectangular face, and it is represented as capital A. So we know that stress is equal to resistance offered by the body to the unit area. So we know that when we apply a force, the same amount of resistance will be offered by the body. Then only the body will be in equilibrium. So that means the resistance offered by the body is same as the external force. So I can write this equation as stress is equal to external force P divided by unit area. So that means it is sigma is equal to P by area. Usually stress is represented using this sigma, and here since it is a force acting on this member is tensile in nature, we are representing this sigma with a suffix that is T. That means it is a tensile stress sigma T, that is equal to P by area. Now we have this compressive stress here. The same rectangular bar is considered here again, and this is the area of cross section we are having, and this is the external force that is acting on the component. But here the nature of the force acting on the component is compressive, and the area which is resisting the compressive force, it is this rectangular surface, and that is having an area of cross section capital A. So since it is a compressive stress, I can represent this as sigma C, meaning it is a compressive in nature. The stress is compressive in nature. So we can represent this as sigma C is equal to external force P divided by capital area. Now always we have to remember that if we are applying a force in and the magnitude of the force is in newtons and the area of cross section is in millimeter square, that is the side is expressed in millimeter, this will be in millimeter and this is in millimeter. So that means the area is in millimeter square, then the unit of stress, it is equal to Newton per millimeter square. Now we have the shear stress here. For that I am considering a rectangular section like this, and we are having an external force P acting in this direction. So we can see that it is the force, external force acting on the member is tensile in nature. So it will be producing a tensile stress along this surface because the force acting on the surface is exactly perpendicular to the surface. So here we will be having a tensile stress. But if I consider a plane like this line, we will be having two types of stress acting along the surface. And first let us consider this plane, this surface is making an angle of theta with respect to the vertical line. With respect to this dashed line, this surface is making an angle of theta. So, this surface will be having two types of stress. One, it is a normal stress, and the other one, it is a shear stress. Now, how that is happening? Because if I consider this force acting here, I can resolve the forces, that force, into two components. This horizontal force can be resolved into two components. That is, one component which is perpendicular to this surface, and that is represented here as sigma theta, and one component which will be along the surface, and that is represented as tau. So that means shear stress, the stress that is acting along the surface. So that is always represented as tau. That means it is the shear stress. And this too can be found out by using this equation. Sigma theta is equal to P cos theta by A by cos theta. And we know that sigma is equal to force by area. And shear stress is equal to P sin theta by A by cos theta. Here also shear stress means shear force divided by shear area. Now how we are arriving at this equation? Let us see that. Now for that, I am considering this triangular surface, this triangular element. I am considering this vertical line, this horizontal line, and this inclined line. So that means we will be getting a triangular plane. So I have redrawn that triangular element. This is a vertical line, this is a horizontal line, and this is an inclined line that represents the inclined surface, and that is making an angle of theta with respect to the vertical. Now from this figure, this is the direction of the force P. I am drawing that force in this direction, that is horizontal direction, and this is a surface we are considering. We have to find out what is the magnitude of stress and what is the nature of stress acting on the surface because of this external tensile force. Now, as I said earlier, we can resolve this force P into two components. One, it is a perpendicular component. If you see, this is a perpendicular line to this surface, and then this can be resolved into a horizontal component, that is this red line showing along the surface. So this is a normal component and this is a tangential component. That means this normal component is always sigma, and this one, it is a shear. Now let us see how we are getting this angle in this equation. Now first let us consider this side. This side is represented as A, and let us represent this side as B, capital B. In that case, cos theta will be equal to capital A by capital B. So I can write this B is equal to A by cos theta. So this means this is the area of this side B. Now I can find the force acting along this direction, that is in the normal direction, and what is the magnitude of force acting in the tangential direction. So for that, here we know that this angle is theta. So if I draw a line parallel to this vertical line through this point, I will be getting this vertical line which is drawn using the green color. So this angle will be same as this angle theta. So here also we are having this angle theta. Now we know that this line and this line is making an angle of 90 degree. So that means if this angle is theta, we will be getting this angle as 90 minus theta. And we also know that the normal component and the tangential component will be making an angle of 90 degree. So if this angle is 90 minus theta, we will be getting this angle as theta. So the angles are obtained. Now we have to resolve it. Now we can take this force we can resolve this along this direction. So that means the force acting along this direction is equal to P into cos theta. That is written here, P into cos theta. The force acting along this line, you can resolve it in this direction, that is P into cos 90 minus theta. That is P into cos 90 minus theta written here, which is equal to P sin theta. So the force acting along the tangential direction is equal to P sin theta, and along the vertical direction is equal to P cos theta. So I can write it as sigma theta is equal to the force along the vertical direction, that is in this direction, which is equal to P cos theta divided by the area of cross section of this side becomes equal to B is equal to A by cos theta. So that is how we are getting this value, sigma theta is equal to P cos theta divided by A cos theta. And if we consider the shear stress tau, here the shear force magnitude we have found out as P sin theta, and the area is equal to A by cos theta. That is other dimension, we are taking it as 1 millimeter. So here I can write it as tau is equal to P sin theta by A cos theta. This is how we are getting this normal stress and tangential stress. So in this session we have seen the simple stresses such as the tensile stress, compressive stress and shear stress which is acting on a machine element. Thank you.